So Professor Kristin Lauter is a mathematician and cryptographer doing research in number theory, algebraic geometry, and application to cryptography. She is particularly known for her work on homomorphic encryption, elliptic cryptography, and post-quantum cryptography. She is a principal researcher and partner research manager of the Cryptography and Privacy Group at Microsoft Research in Redmond, Washington. She served as president of the Association of Women in Mathematics, AWM, from 2015 to 17. She currently serves on the board of trustees for MSRI. She is a fellow of the Mathematical Society's SIAM, AWM. She is the Poliel Lecturer for the Mathematical Association of America, published more than 100 papers, holds more than 50 patents. So we are delighted to have Professor Lauter here. So Kristin, you may start.
Thank you so much. There's an echo. Now let's see. Yeah, great. The echo is gone. So hopefully you can all hear me and you can see my slides. I guess I might have to be a little brief since we started a little late. I'm so sorry about that, the internet connection problems. But please tell me about 5 or 10 minutes before the end. So I definitely want to show the demos of the technology at the end so everybody can kind of get an idea of seeing them working in action. So I'm going to talk today about private AI, about machine learning on encrypted data. And this is joint work with all of the researchers in my team and our partner engineering team at Microsoft Research, and represents work that we've been doing over the last 3 to 5 years at least. So when I say private AI, what do we mean? What's the privacy problem with AI? So artificial intelligence uses machine learning algorithms to make useful predictions. The idea is that you input your data and the system takes your data and inputs it into some mathematical function and outputs some recommendation or decision or classification. And that's the prediction or inference stage of machine learning and AI. And you can see what the privacy problem is, and that is you have to input your data in order to get your prediction. So if that means, you know, you're walking around with your smartphone and you're getting, you know, recommendations on directions or nearby restaurant recommendations, or if it could be, it might be something, you know, more serious and more sensitive, such as your health data or your financial data. But in either case, sharing a detailed location data with the cloud or your health or financial data can be problematic because this data could be aggregated over time and you don't exactly know how this data will get used in the future once it's collected. So that's kind of from a consumer point of view, but about the prediction stage. There's also, from the consumer point of view, about the training stage. So there are a lot of machine learning algorithms for different tasks that have been trained. The way the training stage works is, again, an entity collects a large amount of data, and the data scientist or the person who manages it tries to decide on the best, you know, mathematical model or algorithm to use to make the prediction, and they actually have to train that model on a large set of data. So again, you have the same privacy problem that you're using a lot of consumer or customer data in order to train the model. So I like to give a few examples of the different types of privacy problems that can arise when using private data. So these are just news clippings from last year, from 2019, where privacy became an issue. So for example, the city of Los Angeles is suing IBM, the IBM weather company, over deceptive use of location data. And there's numerous other stories such as that, where data was collected apparently for one purpose, but then it gets used for another purpose. So today I'd like to talk to you about a mathematical tool for protecting privacy and security of your data through encryption. So the idea is that for outsourcing of computation, or for making a request like a prediction, that you need you need encryption that you can compute on, homomorphic encryption. So I'm going to tell you a little bit about homomorphic encryption, which you may know already about, but for those of you that don't. So the idea is that homomorphic encryption allows you to, I have a one-sentence definition that I like to tell. It's an easy way to remember what is homomorphic encryption. It's encryption that allows you to exchange the order of encryption and computing. So you can either encrypt the data and then compute on the ciphertext, or you can compute first on your data locally and then encrypt it. And in either case, you should get the same answer when you decrypt it. So just a note about the type of encryption here. We always use randomized encryption, which means every time that you encrypt a ciphertext, you'll get a different looking, every time you encrypt a plain text, you'll get a different ciphertext, and you should not be able to tell whether two ciphertexts are the same. But when you decrypt them, in this case, you should get the same answer. And we need to use randomized encryption to avoid things like a dictionary attack, where somebody can encrypt known plain text and compare them against encryptions and see what the encryption was encrypting. So homomorphic encryption was an open problem for many decades, and the first real general solution was proposed in 2009 by Craig Gentry, but was considered completely impractical. In 2011, researchers on my team at Microsoft Research came up with a new homomorphic encryption scheme, which was both tied to known hard problems and also certainly implementable and practical. So given that there were mathematicians and computer scientists on my team, we were able to quickly work together to make a lot of improvements to this scheme for practical use. So we introduced techniques for practical encoding that led to big speedups. And we started to be able to show being able to do machine learning tasks on encrypted data. So first, before telling a little bit more about the machine learning, first let me tell you a little bit more about the mathematics of homomorphic encryption and how it works. So in the period from about 2004 to 2013, there were a number of different hard problems that were investigated and schemes that were developed based on these for doing homomorphic encryption or in general lattice-based encryption. And these were the small principal ideal problem, approximate GCD problem, learning with errors, ring learning with errors, and these are all related to well-known hard lattice problems that have been around for more than 30 years. But lattice-based cryptography was actually proposed by Hofstein, Pfeiffer, and Silverman in 1996 with the ntrue crypto system, and also separately and independently by Itai and Dwork. So think about it as having been proposed in the mid-90s, which is about 25 years ago, versus some of the other practical, mathematical-based public key encryption schemes that are used today, such as RSA and elliptic curve cryptography, ECC. These are both widely deployed in the industry worldwide. And these are roughly 35 and 45 years old, respectively. So, but 25 years old is not too bad, especially because the lattice problems, particularly the approximate shortest vector problem, and the bounded distance decoding problem have been around for even longer than that. For example, a fairly well-known algorithm for lattice-based reduction called LLL has been around for more than 30 years. And it's actually a polynomial time algorithm, but it gives you an exponentially bad approximation to the shortest vector. So LLL has been around for more than 30 years, so you can tell that the lattice reduction problem has been around for at least 30 years. And the community has developed a number of other tools for attacking lattice basis reduction problems. And there's an active community of researchers working on LLL and extensions such as BKZ, BKZ 2.0, and also exponential techniques that are used as subroutines such as sieving and other types of strategies. But all of these together today result in attacks on lattice-based crypto systems, which take exponential time. So exponential time in the dimension of the lattice. So if you see me use the letter little n for the dimension of the lattice, the best attacks take at least 2 to the n time, which makes them fairly secure when n is a lattice of dimension, 1,000 or something like 1,000 is the minimum that we use for homomorphic encryption. And the other key point is so far they're secure against quantum attacks. There are not known polynomial time quantum attacks to attack these systems, which also makes the homomorphic encryption, everything I'm talking about here today, what we call post-quantum cryptography or post-quantum secure, at least for now. So I'd like to just give you a very brief idea of what a lattice is and how it gets used in cryptography. So you can think of a lattice as just being a discrete linear subspace of Euclidean space. Here I've just shown it in 2 dimensions. So it's generated by 2 linearly independent vectors. Here I've shown 2 vectors B1 and B2. Which are linearly independent, and they generate a rank 2 submodule. And you can see that, or rank 2 vector space, you can see that these 2 vectors, B1 and B2, are relatively short. They're relatively of the same length. And it means that if you took a random point in this lattice, and you were trying to express it in terms of these 2 vectors, it would be pretty easy because you would just kind of go along over here until you got to this, this amount, and then you'd go up this way until you got to this amount. So you can kind of see it's pretty easy to decompose things when you have such a nice basis for your lattice. So now let's look at the same lattice but with a different basis, which is the basis vectors B3 and B4 are longer and they're more skew. And you can see that if you take a random lattice point like this one, it's a little bit harder to figure out how to express it in terms of these 2 basis vectors. And so now, stretch your imagination and think of vectors that are the basis vectors, and they are extremely long, like they go halfway around the planet or something like that. And they're also very skewed. So you can imagine it would be difficult to think about how to express other vectors in the lattice in terms of those 2 vectors. Now, I've just shown you a picture in 2 dimensions. This is a little bit deceptive because in 2 dimensions, lattice basis reduction is actually very easy. There's the Gram-Schmidt orthogonalization process, which allows you to just project one vector onto the other and then subtract, and you just iterate that until you get down to 2 short vectors. So in 2 dimensions, this is easy, but now imagine n dimensions where n is very large. So think of n as being like around 1,000. So LLL algorithm suggested taking actually blocks of k vectors at a time, not just 2 vectors, but even k larger than 2, but less than n, and doing kind of an analogous process to Gram-Schmidt orthogonalization in this block of k vectors and successively reducing down until you can get short vectors. So that's roughly speaking how LLL works. But it still, as I mentioned, remains a hard problem in general to find the shortest vector or even to find an approximate shortest vector for certain approximation factors. So now I'd like to take a few minutes and just explain how encryption works with this lattice-based system. So encryption works by blinding a message with what we call a secret inner product plus some noise. So blinding, encryption through kind of blinding is a very standard technique for encryption, going back to even like a one-time pad where you take a message and you just blind it with a bunch of random bits. But that doesn't give you any nice, homomorphic properties, and it also has a lot of other disadvantages, such as requiring very long keys, at least as long as the message, and the transmission of keys is difficult. It's a symmetric key system. So to come up with a nice solution for homomorphic encryption, what we do is we try to make a kind of a blinding of the message, which is a bit more algebraic and retains the algebraic structure in the encryption. So the way that we do that is in the vector space, which is the lattice that I showed you, the encryptor will, the data owner who wants to encrypt a message will take a secret vector, and then every time they want to encrypt something, they'll generate a bunch of randomness. And they'll take the inner product, the randomness will also be random vectors, and they'll take the inner product of the random vector with the secret vector. So that gives you something that you can use to blind a message. The message will also be transformed into the message space. It'll be transformed into a vector in the vector space in the lattice. And then what you'll do is you'll simply add this secret inner product to the vector. So the idea is that if you only did that, if you only added secret inner products, then you would be left with a system that somebody could break by using linear algebra if they've seen a lot of encryptions of your messages. So instead, what the encryptor does is to add some noise to the message plus the secret inner product. And what that does is it makes it so that the hard problem that needs to be solved is basically decoding noisy vectors. If you do have a short basis, it's fairly easy to decompose vectors and find the shortest vector and find the closest vector and kind of cancel out the noise. But if you don't have a short basis, then it can be very difficult to solve this problem. So we end up with an encryption scheme that is based on the hardness of lattice reduction, and but the decryption works fairly easily because the decryptor, if they have the secret, and they know the randomness is sent with the ciphertext every time, they can just subtract the secret inner product, and then the noise is small, and so it becomes very easy to cancel. So one other note that I'd like to make here is that in practice, what we do is instead of thinking of these as lattice vectors, the coordinates of the vectors are thought of as coefficients of polynomials, and polynomials can be added and multiplied together. So in fact, ciphertexts and all the operations on ciphertexts in practice today are all done on polynomials in certain polynomial rings. And I'm not going to get into more details on that just now. So the one other thing I'd like to emphasize about homomorphic encryption and the current solutions is that the main problem, well, there's several big problems, but one of the big problems is the noise that you add to a single ciphertext. When you add ciphertexts together or when you multiply them, that noise will grow. And so you can see in the upper right-hand corner here that when multiplying ciphertexts, the length of this red arrow pointing down here represents the size of the error after you've multiplied, the noise after you've multiplied two ciphertexts. And as you can see, the noise grew so that actually this point is closer to this lattice vector than it is to this one. And so it would decrypt incorrectly. So what you have to do, and especially initially, we spent a lot of effort to do parameter selection and kind of tuning the system so that you don't kind of exceed your ability to decrypt correctly. You don't do more computation than the system can handle. So practical homomorphic encryption was my term for what we did early on, where we used all of the coefficients of a polynomial to encode data such as integers, using like the binary representation of an integer or floating point to actually put real numbers into the polynomial ring directly, instead of the previous approach, which had been just to encrypt data bit by bit. This allowed a lot of practical computation on real data, including health data and certain machine learning computations that we were able to demonstrate. And also, just another note is that in everything that I'm showing you today and everything that we've implemented and done so far with homomorphic encryption, we do not use bootstrapping. Bootstrapping is a costly process that was introduced in the initial paper by Craig Gentry, which allows you to basically re-encrypt ciphertext to make the noise, to kind of dampen down the noise so that you can continue computing. And we have found that much more efficient to just do computation up to a certain depth of circuits instead of to actually use bootstrapping in our computations. So already in 2012, we were able to show machine learning on encrypted data. We had showed the first paper showing training of machine learning models, very simple machine learning models, but we proposed the concept of polynomial machine learning, which is approximating machine learning algorithms by polynomials. And one of the kind of most successful examples of that was that, so in 2016, in our CryptoNets ICML paper from my team, we showed that we could actually evaluate deep neural nets on encrypted data using a polynomial approximation for the activation function in the layers. So a typical activation function is as shown here, and it's could be approximated. We looked at different approximations such as the Taylor series around 0, or other polynomial approximations such as the Chebyshev polynomials, but in the end, we actually just used the approximation function, which was just x squared. So we're able to take a kind of melding cryptography and machine learning research and show that we could get good results on predictions using complex neural net, machine learning algorithms, and apply them to homomorphically encrypted data by approximating the activation function with a polynomial function. So there's been a lot of follow-up work since then by many teams, including research teams from MIT, UCSD, UC Berkeley, and Seoul National University, and startup companies in industry, showing that neural net predictions can be done extremely fast, even for very deep circuits. So I'd like to talk a little bit about the practical applications, collaborations with machine learning researchers, bioinformatics, and finance. So the first kind of demo that I showed live of homomorphic encryption was back in 2014. So machine learning models for predicting whether you'll have a heart attack were developed in a decades-long study called the Framingham Heart Study. So there's publicly known models that will predict your likelihood of having a heart attack based on 6 characteristics about your personal health data. So your weight, your age, your height, your blood pressure, body mass index. And so what I did is at the AAAS meeting in Chicago, so AAAS is the American Association for the Advancement of Science, and they really focus on public outreach. So they had a lot of news reporters in the newsroom, and I showed a live demo of predicting my likelihood of having a heart attack based on my private health data, using the cloud, but using having the cloud do the computation on encrypted data. So I input my private data into my laptop, and of course I kind of spoiled the whole point of it by sharing things like my private data, like my weight and height and age with everyone, but just to kind of show the technology in action. So on my laptop, the data was encrypted, and then it was sent up to the cloud. And so this was encrypted using homomorphic encryption, and the software in the cloud is the same software that was used to do the encryption on my laptop, so the parameters matched and everything. And the cloud does the computation, and then the cloud sent the prediction back to my laptop, and I decrypted it locally. So, and that whole process took 0.2 seconds, including the round trip communication costs. So at that time, that was especially surprising to people who thought that homomorphic encryption was extremely impractical. And this was a non-trivial machine learning model. It was something like a Cox proportional hazard method with, using a polynomial approximation. So since then, we've worked a lot on genome privacy, genomic computations, and being able to enable genomic computations on encrypted genomic data to do things like data quality testing, basic statistical functions, and things like predictive models and string matching or sequence matching or edit distance. So focusing on, health and genomic privacy, we showed, again in 2014, a number of different algorithms, genomic algorithms that could be evaluated on homomorphically encrypted genomic data. And we got involved. I personally have been very involved with the NIH IDASH competition for secure genome analysis for the last 5 years or so, where and NIH is the National Institutes of Health in the US, and they've been funding this competition that brings together teams from around the world to compete to show how fast certain tasks can be done on homomorphically encrypted data. And they have other tracks on other privacy topics such as secure multi-party computation, MPC, and differential privacy, DP, and hardware-based solutions such as SGX. But in the homomorphic encryption track over the last 5 years, you can see the different tasks that have been used for the challenges and the contests. And my team won the competition the first 2 years, and we've been participating in the evaluation and helping with the competition in the subsequent years. So even things like training logistic regression logistic regression models are possible and practical on homomorphically encrypted genomic data. So I'd like to kind of skip to giving you a little bit of information about the commercial deployment and a lot more relevant information if you're interested in using homomorphic encryption today in any one of a number of contexts. So based on our early work, what we decided to do, we actually got a lot of requests from people in the bioinformatics community. Could we create a library or a tool that would be broadly usable by developers and people in other communities such as bioinformatics that could be used to homomorphically encrypt sensitive health and genomic data? So that kind of motivated us to develop the simple encrypted arithmetic library, Microsoft Seal, and we released it publicly in 2015. It's been widely adopted by teams worldwide, and to the point that we decided in 2018 to do an open source release of Microsoft Seal, so that the technology is now freely available for commercial use You can download it. You go to sealcrypto.org if you want to download the code. You can work on it. You can contribute back to it. And so it's now a massive open source project, including other third parties who have used it to build and deploy more complex solutions with using SEAL as the underlying homomorphic encryption engine underneath. So the other point that I wanted to emphasize is that when you introduce a new encryption technology, it also needs to be standardized. Because how is the public supposed to trust what are the parameters that you chose? How do we know how hard these problems are? These are new hard mathematical problems. So starting in 2017, at Microsoft Research, I co-organized a series of workshops leading to the standardization of at least a preliminary standard for homomorphic encryption, which sets the security levels and the parameters that can be safely used to achieve certain security levels. And the draft standard that we wrote based on our initial white paper from the conference has more than 15 co-authors. It's available on ePrint, and it was approved by our community in November 2018, so 2 years ago. It's been referred to by many different communities and documents since then. Another thing I wanted to kind of point to is the status of commercial deployment. So at Microsoft, actually going back to 2018, our CEO, Satya Nadella, gave a talk at our big developer conference, Microsoft Build, which was covered by Fortune magazine. And here you see the story from Fortune magazine with the quote, where he said that privacy is a human right, and that he was pitching a way for companies to learn and train on encrypted data using homomorphic encryption. So that was great. We've talked to a ton of customers since then. And what we've actually been able to release publicly is in Azure ML, announced at Microsoft Build in 2020, we've actually released private prediction notebooks. So you can actually go to the Azure ML page and find private prediction notebooks for evaluating like linear or logistic regression models using SEAL. So you can upload private data in encrypted form and have predictions made and returned to you. I'm going to show you a few other demos of other types of services that we're building. Yeah, so this is the standardization community that we've formed. More than 200 researchers worldwide participate in regular conferences. We've been a little bit slowed down since COVID. We had, I think, 6 conferences up through February of this year. And there was a conference planned in Geneva, co-located with the UN AI for Good conference in May that had to be postponed. And so we'll have to wait and see when our next in-person workshops are going to be. But it's a large community working on the standardization of homomorphic encryption. The community also keeps track of and advertises many different homomorphic encryption libraries that have been developed around the world, from HElib at IBM, which was an early library widely used by researchers. SEAL, as I mentioned, is a very well-engineered library, which is very robust and used by developers worldwide. The NFLib library from the European Heat Project, Palisade, developed by the startup company Duality, special purpose GPU implementations such as QHE, and then the Seoul National University library, which supports approximate computation, called Heian. And finally, a different approach, which is bootstrapping after every gate with the FEW or TFHE libraries. So a lot of people think that homomorphic encryption is extremely impractical, and this shows how much better it's gotten over time. So when we first started working on it, it was estimated to have an overhead of about 10 to the 13. And now we estimate that overhead to be somewhere around 10 to the 4. So something like between 1,000 and 10,000 times slower than plain text operations. But that's fairly reasonable for a lot of tasks. If you have a task that you were doing in microseconds and it now takes milliseconds, that will often be tolerable. The dotted line at the end of this chart is for the kind of hardware acceleration that we can get for using GPUs or FPGAs or special purpose hardware. So here are just some of the performance numbers, just so that you get an idea of the absolute numbers here. Even in a fairly small dimensional lattice from our point of view is something like dimension 4096. So if you look at this first row here, you can see that like the amortized multiplication time for multiplying ciphertext is like, you know, 1/4 of a microsecond. So that's pretty good. So I think I'm going to skip to the demos now so that I can show you some applications of homomorphic encryption running in practice. I've done over the years a series of different kinds of demos built by my team, starting from the heart attack risk prediction that I talked to you about in 2014. CryptoNet's demo that we showed handwritten digit recognition, the MNIST data set. We've done genomics and health predictions, and even Twitter sentiment analysis and image image classification, classifying pictures of cats and dogs. So it really is a broadly usable technology, especially for prediction. Training is still an ongoing area of research because of the large amount of data that can potentially be needed for training and ongoing training, but we have strategies for addressing those kinds of challenges as well. So I'd like to show you today our demos from just this last year, which address some of the privacy concerns that you saw in those newspaper articles in the first few slides of my talk. So the first one is a private fitness app. So for any of you that wear a fitness tracker for keeping track of your activity, your walking and running, the problem with the fitness tracker is that your location gets uploaded to the cloud, and you know, any kind of analysis that's done on it is done in the clear. Well, what we wanted to show is that you could have a private fitness tracker which only uploads encrypted data. So what we're showing here is a video of the demo. This is not a live demo, it's the video of one of our team members walking around in our building. And you could see that instead of the app sending the location and other data about his activity to the cloud, you can see over here on the right that it's only uploading encrypted versions of the data, the location and accelerometer and gyroscope information. And so then what happens is once the run is complete and you want to ask for a summary, for example, how intensive was my workout, this is like a simple machine learning computation, and that can also be processed on encrypted data, just like I mentioned the heart attack prediction risk, it could be processed. So right now what it's doing is it has processed the prediction on the encrypted data and sent it back, and now it's decrypted locally to say that, oh, that was a medium intensity workout. So the Azure Run is actually available, but it's not a commercially released fitness tracker. Instead, it's an app that shows developers really how you can develop private apps using Seal. So just, I guess, one note of caution is that it's built on an earlier version of Seal. The next version of SEAL is about to be released. It's version 3.6. And the SEAL library is owned and managed by our lead researcher and developer, Kim Lina. So next, I'd like to just show you a quick demo of chest x-ray. So this is a medical application again. So suppose you go to the doctor and you have some illness and he or she wants to upload your chest x-ray to get an analysis of what what it looks like, what disease you likely have. So what the doctor has already uploaded it and received the encrypted prediction back from the cloud and has now just decrypted it locally. So you could see that was almost instantaneous, and that allows a doctor to consult a real-time service, but without sharing the patient's sensitive data with the cloud. Only encrypted data was shared with the cloud. And so finally, here's my last demo. Don't blink or you'll miss it. It goes by very quickly. This is a secure weather app. So it's already returned the prediction. What happened was that I input the zip code. This is in the US. I input the zip code 98052, which is for Seattle area, to ask for the weather. And you can see the weather data is already returned. And what happened in the back end is that encrypted data was received. It was compared against a whole database, and an encrypted aggregate was computed and shared back to the user, which was decrypted to show just the weather in Seattle. So the cloud had no idea what location was requested nor what data was returned. It just it touched every item in its database and it returned an aggregate of encrypted data. So that was to show you that we could also achieve privacy in things like, a secure weather app, which today uses your location data in order to tell you the weather. So in conclusion, I'd just like to say thank you very much for listening. I'm sorry for the technical problems. I hope we still have a few minutes for questions. And in summary, my talk was aimed at showing you that there's a new mathematical tool, homomorphic encryption, which is actually quite practical, that can be used to do all kinds of machine learning tasks, from prediction to training. And by using homomorphic encryption in the future, I hope we'll use it more and more. We can protect private consumer and enterprise data while being still used for purposes such as training or prediction. So thank you very much for your attention.
Well, thanks a lot for this nice presentation, Kristin. Let me see. We have open for questions right now. Yeah, so let's start. Let me put here. I'm going to read to you, okay?
Great.
So the question is from Carlos Gallardo. I would like to know about side channel attacks over lattice-based homomorphic encryption and computational costs to protect them. I'm concerned with the adversary capability to have access to the client system with the encryption takes place. In worst case scenario, the adversary could be the company who built the client system, as Google Android, Microsoft Windows, and Apple iOS.
Yeah, so I think that one thing I haven't distinguished between the public key and the private key setting, and there are differences in the sense that in the public key setting, anyone can encrypt to the public key, but not decrypt, of course. But in the private key setting, which is really perfect for outsourcing, the person who wants to have the service performed on their data does the encryption. And so the side channel attacks are not really much of an issue in that case. But there are other issues, which is that if you have a malicious cloud, which instead of implementing a safe protocol, actually creates a way of learning kind of auxiliary information by interacting with the party who has encrypted the data, that can really open it up to major security flaws. So an example of that would be like receiving ciphertexts from the consumer, and then sending back a response which says, oh, there's something wrong, can you please answer this question. And this type of interaction could lead to security vulnerabilities. And so the problem is for services, especially big companies have no incentive to start, to stand up malicious services. But other companies might have an incentive to stand up malicious services which impersonate the services of Microsoft or Google or whatever. So that is an ongoing area of inquiry. So in general, what we worry about, like side channel, usually when there's some kind of attacker that can observe, that can snoop on the encryption process and can see the noise or the randomness that is added in generating a Diffie-Hellman key or something like that. But that's not really part of the setting or the threat model for the simple application of outsourced computation.
Okay, there are many more. So let's go to the next one. Fabio is asking, how about the performance of squaring activation function for neural networks?
Yes, so I didn't show the detailed performance, but it's very good. So like squaring activation function is really easy, to implement, and it doesn't add too much depth to your circuit. You do it at every level, but it doesn't add it, it doubles the depth. But so we have even experimented with linear activation functions with different constant terms and things like that can still achieve relatively good accuracy in neural nets. But the whole point is using the square activation function, eliminates the need to have a much higher degree approximation of the sigmoid, which is kind of a smoothing of the max, the zero max function. So performance is good. So if you look, I actually have a slide that I didn't show that shows CryptoNets, which was from 2016 with the version of SEAL that we had at that time. It's been improved. The CryptoNets performance has been improved by orders of magnitude just using the new version of SEAL. But in addition, there's many other, if you want to see current performance numbers for that kind of thing, for using square activation function in neural net predictions. You can look at the other projects that I mentioned. You can look at the papers from MIT, like the Gazelle project, from UCSD, Deep Secure, from the Heian project at Seoul National University. So all of these, and the Lola project. So all of these are more recent papers, and they have very recent up-to-date performance numbers.
Okay, next, Robson Albuquerque, and thanks your talk. And he asks, do you know if HE is already in relational database or in NoSQL database?
As far as I know, it's not already in use, but it's certainly, we have certainly experimented with showing different types of queries that can be answered. I can tell you one of the challenges with like SQL type queries is that not all of the queries are equally well suited to really efficient practical performance. The fact is that what I showed you examples of today was a lot of computation which takes like floating point numbers or, real computation, like practical computation on real data, which we often call like arithmetic computation. Whereas logical computation, meaning where you have bits of data, like for example, genomic strings, or you want to do tasks like comparison. When you want to compare two numbers, you represent them with bit strings, and then you compare the bit strings, and each of the bits is kind of handled separately. The logical computation is much more efficient with like the TFHE library that I mentioned, and the TFHE is not even in the same realm for doing arithmetic computation. And so there's been some work to be able to convert between these two types of ciphertexts, but it's very costly right now to convert between them. If you could convert between them, you'd be able to handle most SQL queries fairly efficiently. But today we're left with this situation that if you encrypt things in one way, some of the queries will be very efficient for that type of encryption. And if you encrypt them using the different scheme, like the TFHE scheme, the comparison and the logical computations will be very efficient, but neither one will be very good at doing all computation.
So Bernardi Nunes asks, what is the most complex model that has been used with recent homomorphic encryption? Is deep learning out of the question?
Deep learning is not out of the question. So we did, I'm not remembering the precise numbers, but we had a paper with our team from 2019, I think, called CHET, C-H-E-T, that showed, I think it was like image at 20 maybe. So certainly we have done neural net predictions of models that had at least 20 layers, which is pretty significant. And this is without bootstrapping. So this is, we initially maybe didn't think that we could make it quite up to that level. So now how to go beyond that? Certainly, using bootstrapping is an option. Also, there are other, innovations that we're looking at. But I always like to take kind of a practical approach instead of just heads down in the rat race, like what's the deepest model you can evaluate. I like to think about, what is the task and what is a lot of work is being done by researchers in ML. What is the best model to use for a given task? Do you really need something that's that deep? We know that often very deep models can be approximated with shallower models which are wider. And so I think that instead of spending too much effort on just trying to figure out, heroic ways to get to 50 layers or 100 layers, rather than doing that, I think it's better to think about, what is the best model for your computation. And most likely we can handle at least the prediction task with homomorphic encryption already today.
So Otto Carlos asks, how you control the number of multiplications because it increases with the noise. Can you use ML algorithm that results in large polynomials?
I'm having trouble understanding the question.
Okay, he seems to ask about the complexity of multiplications. It seems that he says that the number of multiplications increases too much when you have noise, the noise.
Oh, I think I understand your question. So I'm sorry for not explaining this a little bit better, but so when I talk about the depth of a circuit or the number of layers in a machine learning model, that's proportional to the number of multiplications. So what we mean by the depth of a circuit is how many multiplications do you have to do on top of each other, not in parallel, but you take the result of a previous multiplication and you do another multiplication on top of that. So the depth goes up as you have more successive multiplications. And so when we talk about the layers of neural nets, those are, everything I was just answering in the previous question was exactly about that. And even without using bootstrapping, we can evaluate neural nets up to even like 20 layers, which is fairly significant. But as I said, it may even be better to approximate such models with shallower models, which means fewer multiplications. That makes them more efficient for homomorphic encryption.
Okay, so Tiago Souza asks, how fast is the Seal crypto.org library in comparison with the TFHE? I think the TFHE computes every binary gate in around 0.1 seconds. In addition, does Seal crypto.org allows the computation of general functions?
Yes, so that's a good question. I'm sorry if I wasn't clear enough in my explanations. So both Seal and many of the other libraries, including Heian, are very optimized for doing all kinds of arithmetic computations, which means you can encode like real data, such as floating point data, into a single polynomial. And I showed the performance numbers for Seal, where you have like 2 ciphertexts that can be multiplied in, for example, a quarter of a microsecond. So so literally like 4 million times faster than TFHE, like 2 to the 22 faster than TFHE. So what TFHE gets you is TFHE can do general circuits. And in particular, that's what I was trying to say about the SQL databases. When you have things like comparison, so let's say that you have like 2 numbers on the order of, well, 1 million, that takes, 20 bits to represent. So you have a comparison of 20 bits. That's like, 20 operations. And, if it does take you 0.1 seconds, then, you're talking about doing that in 2 seconds. That's really, really efficient. And in general, the TFHE papers show, very, very efficient comparison of even, longer bit strings. So there are certain tasks. What I'm saying is that most tasks, you absolutely would not want to use TFHE, because it's, like I said, like probably more than 2 to the 20 slower. But in some tasks, you would prefer to use TFHE because it would be so much faster. So in the SQL database setting, it would be really nice if we could use both types of encoding and encryption schemes, and then to be able to convert between them, which we know how to do, but the process is very costly.
We have to leave the room now, so I thank you a lot, Kristin, and thank you very much for your time and for this nice talk. Unfortunately, we have to leave.
Yeah. Thank you so much. Enjoyed it very much.
Bye
Have a nice
now.
day. Bye.